All right. Okay.
All right, ready to get started?
Okay. Wrap. Yep. Yeah, I think we can getting started. All right.
Okay,
I'll
do you guys want to
be
do a quick introduction on your side?
okay. Sure. So we're team 204, Chulalongkorn University High Altitude Research, and yeah, we'll be competing in the 30K COTS category. This is our fourth vehicle of the club, and yeah, I'll pass on to flight dynamics team to like go over some basic parameters. Then we'll be start talking on the structures, then the recovery, the avionics, and uh yeah, some payload brief, and like we'll go on the air brake, respectively.
Okay, sounds good.
Right.
Okay, hi, my name is Apivit. I am the head of flight dynamics. So first off about the rocket. So this is our first rocket. It is 2.9 meters in length, and we are expecting it to reach an altitude of 29,000 feet with the air brake system activating. So it actually goes around 29,900, around 30,000, but we are targeting to be 29,000 with the use of air brakes. And yeah, stability is 1.5 caliber and maximum is 4, so we are expecting a stable flight. Yes. Okay.
จอสไลด์ก่อน
ต่อเลย
น้อง pass on
Okay. I'll pass on to structures ใช่ไหม Yeah, structures.
Okay, do you want us to begin the mobile camp?
Yeah, if you want to start doing like a structural overview and kind of point things out and show it off as you go.
Okay, sure. We'll be doing from I think tip to the thrust plate.
Yeah, sounds good to me.
Okay.
Okay, okay. Our consumer rocket is divided to four sections. For the node core section, main section, airbag module, and the booster section. Okay, let's start at the top of the rocket. The hot aluminum tip. We use the tip from the Russia rocket. This attached to the M8 stud and secured by ball head and eyeball inside the node core section. So this is a Wyman rocketry fiberglass node core section. It have a carbon shape. Okay, this section have a main and low pressure inside for the recovery system. And then we have the full of M4 shear pin for separate the node cone. The 6-inch copper inside the node cone is combined with the node cone by the rocket proxy. Okay, let's move to the main section. In the main section, we have this section composed of recovery bay and the payload bay. First, the recovery bay is made by 3D print ABS plastic. The PCB board, chain battery, and eagle and the recovery system attached to this bay, secured by two MS stud and the ball head top and the bottom. Then the payload bay will hold inside it, hold at the bottom of it. Secured by two ball head and two MS stud, same at every bay. Okay, this section is every module.
Okay. Okay, so the next section of the payload module is the air brake module. So basically, this is the new part, the novel that we are trying to explore this year. So basically, we want to control the maximum apogee of the rockets by extending a simple types of leaf. Let me just show you the image. So basically, it's something like this. So basically, we can extend some aluminum leaves outside of the rocket module. So the drag of the rockets will increase, and we can kind of like control the maximum height of where we want our launch vehicle to be. So, if you look closely, I don't know if we can open this or not. There will be two main sections of the air brake. So firstly, there will be the upper section and the lower section. The upper section is basically an aluminum ring that also works as somewhat of a coupler that helps us connect, the air brake section to the upper parts. Not only that does it help with, the compression and the tension load, it also helps with the bending. For I believe it penetrates about like one caliber length inside. So basically it agrees with the convention. So the upper part and the lower part will be connected by I believe M6 radix joints, which should be able to receive both the compression load and the tension load of the launch vehicle throughout the entire launch period. So now the lower section is where we're going to house the main, mechanisms of our air brakes. So if you come back to the old model, sorry, you can see that the leaves here were propelled, were launched out of the launch vehicle by a gear, which will be connected to a servo motor. Although you can see something like this, the servo motor and the gear actually only uses to extend the leaf outside. All the drags and the air resistance will be received by all the air resistance and the loads, the compression load will be received by two pairs of linear rails underneath the lower section, which will be in turn be attached to a carbon fiber bulkhead underneath it again. So that's the whole working mechanism of the air brake. So if I could demonstrate to you. So basically, if I spin this thing around, it should extend the air brakes outside, and then with a given time, it should retract back. So something like that. And further than that, there will also be this lower tubular structures here, which will be connected to the 5-inch rocket section, of which I will talk later. So the other differences from the past rockets we have is that we have two different airframe diameters. So we have 5-inch and then we have 6-inch. So what we're going to do here is that we use this air brake module as like a connector between these two different diameters. So I'm going to take this thing out again. So what we do here is that the air brake module is a 6-inch module, but it has this extended tube out, which can be connected to a 5-inch airframe. So, sorry. Sorry. I have a bad sleep last night. The launch vehicle will, so the transition works something like this. So there's this 5-inch airframe which will be connected to this tubular structure. So it kind of like works something like a coupler. And then it will be joined with the booster airframe with a facing coupler. If I can see, yeah, there will be some like a coupler inside. So this not only helps with the compression, but also helps with the bending and the shearing of the launch vehicle. Furthermore, the connection from the upper parts of the rockets to the lower parts of the rocket will be connected by a strut from a dedicated bulkhead in the airframe in the air brake section to the motor. So when the parachute ejects and there is some tensions, all the tensions will go directly to the struts, not the external parts. Therefore, we don't need to really link these two parts, say this entire parts, with the booster parts. We just need to connect inside these specific parts together with some, say, epoxy or something like that. if we do something like radial screw, it would take way too much joints and bolts. So we just decided to use an epoxy instead. I believe that's the entirety of the transitions. So next part will be about the boosters.
Okay, for the booster section, it will be connected to the coupler of the booster by radial screws that will, the inside of the motor will be attached with the top of the coupler by a forward closure of the motor. And here is the motor tube we'll be using. It's a phenolic tube that would fit the old 55,000X motor in. And we got like a centering rings. We'll have 4 of these inside the rocket so that it can reduce the vibration from the motor transferring to the airframe here. And next is the fins and brackets. So can you introduce the fins and brackets?
Yeah, so for the fins, this year we chose aluminum 7075 for to manufacture the fins. And we use 6 M4 countersunk screws to attach the fins to the bracket. And so there's the bracket, and we attach them in an alternate pattern. So that way the load will be distributed equally. And we also add this hole here for weight reduction as well. For the attachment of the bracket, we use 8 M4 screws to attach it to the airframe, and we attach them radially inside. Yeah, and lastly, the thrust plate, it's the same design as last year. And additionally, we also add these holes for weight reduction as well. And yeah, I'll pass on to our dynamics team.
So back to the fins. So we have here the fin flutter analysis part, where this is the N2 design. We have used MATLAB codes to determine that it has a safety factor of 1.56. What that essentially means is that it has a maximum it has a flutter velocity of 917.28 meters per second, which already exceeds our anticipated maximum velocity of 588. So this is already great.
Okay, just a quick note. The fins and brackets are at the same batch as the air brake module that we have emailed earlier. So yeah, they'll be arriving at the same time, and yeah, we can send some photos for the updates with you via email. And we have done all the majority slottings with, and we have left some margins at the edges. So when the real product arrives, we can just make it a tight fit as the like a final touch to the margins that we have left.
Is that dark blue piece that's on there, is that part of the flight, or is that just for
No,
holding the
this one
fins
is
on
just
display?
the jig for our slottings and like drilling hole. Yeah, and our brackets will go from the inside and holds the fins.
Got it. Okay, thank you.
Do you have any comments for the structures, outside structures?
Yeah, I do have kind of a few questions going over the sort of entire system, and maybe just to sort of finish up on the motor side. I think I might have missed it, but how are you retaining your motor? Are you retaining it from the aft, or are you retaining it from the forward side?
Okay, so there will be both retainings. So one of them will be at the aft, so like the how the thrust plate works, and another one's going to be from the forward closure of the motor. We'll have a stud up to the dedicated bulkhead around here. Yeah, so we'll be fastening the motor from both the ends and the forward closure.
Okay, and then for the centering rings that are going to go on your motor mount tube, how are you attaching those?
The centering rings.
Yeah, the rings that will go on your phenolic tube there to center the.
They'll be epoxied onto the phenolic tube.
Okay. And then how So you'll need to transport this rocket over to the US somehow. Are you planning on keeping that separation point in the booster section and epoxying it when you get to the US, or are you going to epoxy that before you ship your rocket here?
We usually epoxy it from Thailand, and it usually arrives no scratches.
Okay, good.
Okay.
And then where are your rail button attachment points?
Okay, so our rail button the top one's gonna be at the ABREC module around here, and the another one's gonna be at the very aft end here. And at the aft end, we will have a spacer for the to account for the caliber difference.
Okay, and will you be gluing those on, or will you be screwing those into place?
Yeah, we'll be screwing with two M4 screws.
Okay, sounds good.
You have two different you've got two different tubes for the booster. Is that just because you know it's too long and they don't make it in that length?
Oh, actually, this part's gonna be for the transition. We will have a transition fairing. In fact, we are doing the infusion at the back of our room, back there, for the carbon fiber fairing, and there will be no thrust transferring through the fairing because we'll be just screwing it at the top, and we'll leave the bottom. It will just act as a aerodynamic fairing.
So it'll go over that white piece and onto the
Yes, so it will
black
go
part
from
there?
here and down to around here.
Got it. But you'll be still leaving that other short section of booster tube on the top there?
Yes.
Okay.
But it's going to be permanently fixed together with epoxy in the future, right?
Yes, with epoxy and some radial screws.
Okay. So it's just basically one long tube.
Yes.
Okay.
How far up for the white transition piece, how far into the upper body tube does that part go?
Almost one caliber.
Okay. And is that also going to be glued into place, or are you going to use screws for that?
Again, please.
Are you going to epoxy that, or are you going to use bolts or screws to keep that
There
in
will be
place?
4 radial screws.
Okay.
That's removable so you can ship it, right?
Yes.
Okay.
Are you able to open that section up just so that we can take a little closer look at what that part looks like?
The
Just
module.
at the transition. Yeah, can you separate between the red and the white there?
So it will be removable from both the top and the bottom of that section, right?
Yes, but the lower part where my thumb is now will be epoxied with the airframe when the real product comes.
Oh, so the machine aluminum part is going to be epoxied to the carbon fiber tube.
Yes.
Okay.
So it will be epoxy to this the spacer airframe. Only this part will be epoxy. And the
So
fairing
that machine part and the entire length of the booster will be one unit.
yeah, should.
Yeah.
But
Okay.
we did something like this because it was because the space constraint for our container to ship the entire rocket to the US. So that's why we have to cut it into separate pieces.
So you'll epoxy it only after you arrive in the US?
This part can be epoxy in Thailand. So when we arrive, we can just put the radial screw in and we're good to go.
Yeah, because
About that section all the way to the booster.
yes.
Yeah, the red coupler over there, is that going to be epoxied only in the US?
Yeah, it must be in the US because it cannot get any longer.
Yes, because the green box is our actual
Yeah.
container. Yeah, so it's just the booster long.
Then how are you gonna get it back?
So like
No, อันนี้มัน radial
สองอันเนี้ย so this is the epoxy part and that is the booster and we'll connect it with the radial screw.
Oh,
That's it.
so
Oh,
the
okay.
bottom part of that will be screwed in,
Yeah.
Yes,
On
and that bottom part is removable.
yes,
Oh, okay.
and inside. They do move it. Okay, so this will be the product that we send to the outsourced CNC. Yeah, so it will feature 6 radix joints as mentioned earlier. One of them is inside this white part, and we will have a carbon fiber bulkhead to sit here around these 2 lips, and it will hold the air brake leaves.
Got it. Okay, I see.
And there
Where
will
will the, oh, go ahead.
yeah, there'll just be 2 studs in the 2 holes here.
was connect to the payload above this module.
Yeah, so everything will be connected and preloaded.
Got it. And so for the air brake module that sits in there, will that also include the avionics, or are you using the avionics that are further up in your rocket to control those?
The air brake's gonna have its dedicated flight computer inside this module.
So we'll have a bulkhead here, made of fiberglass, and then the servo motor and the circuit for the avionics of the air brake will be in this section here, including the battery also.
What sort of control scheme are you using to determine when your air brakes need to deploy? Like what sort of sensor inputs are you taking, and how are you deciding when you need to actuate those air brakes?
So our air brake mechanism sensors has many sensors like barometer to measure like the altitude, and then most importantly is the accelerometer, which measures the velocity. So we like use velocity as a main like checkpoint for our air brake to open, because we don't want to open like before like in the transonic or supersonic region. So we use like after 0.8 Mach number only, so we can like get out of the transonic region and not have any like supersonic effects on our air brake, because that was like one of our aerodynamic concerns.
Got it. So will you have then, as part of that control scheme, you won't be deploying your air brakes while your motor is under boost either, correct?
Yeah, that was like way before like we exit transition the transitions like so
Transonic.
Okay. So if you're using a barometer, where is the pressure port relative to where your air brake flaps are coming in and out on your rocket?
Okay, so we will have so there will be one like a major vent through the air brake slot, and we will have a vent hole.
Just a little bit to the top of them?
Yes, because the avionics are located for the air brake computer is gonna locate at the quite top of the upper module.
Have you done any analysis on how your air brakes deploying will influence your pressure reading?
Yeah, if the static is too close to the petals, your reading might get corrupted.
Sorry.
We have done safety.
Yeah, we have done like several like safety analysis on like how the pressure gradients are gonna affect like the pressure zone around the air brake, and it doesn't seem to be an issue.
Okay, yeah, if it looked a little close, kind of like how Julian was saying, if it's too close, then you'll get some weird fluttering effects with your air brakes wanting to come in and out as the pressure is spiking up and down. So if you guys have done the analysis and have proven that that's not going to be an issue, then I'm not too concerned about it, but just wanted to make sure that you've done that analysis and double checked that.
Is your velocity reading using the like some sort of a fusion between the inertial from the acceleration? You're just integrating the acceleration, or are you also feeding in the change in barometric altitude over time?
Yeah, so we use barometric altimeter and accelerometer to sort of get the velocity.
So some sort of a Kalman filter you guys are
Yeah,
using?
we use Kalman filter to smooth out those fluctuations you mentioned. So that might help with the sensor noise.
Okay.
Okay, I think that's all the questions I have on your air brakes, but I'd like to talk a little bit more about your recovery system. Could you point out where, again, your parachutes are in your rocket up in that upper section?
Okay, sure.
Yeah, so I gotta remove this here. Oh. One.
Yeah, so we're removing the M4 share pins. There'll be 4 of them.
That's the one. Okay. Hold on, let me log in.
If we fix some technical issues quickly.
Yeah, there's still quite a few components that are, just 3D printed prototypes or placeholders. I don't know if once the actual thing arrives and you guys actually put it together, if you want to have another review, or if a follow-up email would just suffice.
Yeah, I mean, I would say that assuming everything is good at the end of this review, that emails with kind of photos and just showing everything off will probably suffice. If there's a preference to do another review, I'm definitely open to doing that. I think kind of, yeah, we can maybe decide it at the end of the review here.
Okay.
Okay, so right now we're removing some the bulkhead. So the bulkhead it kind of launches inside the nose cone. Yeah, but yeah, we're removing it right now.
What is on the other side of the bulkhead?
Just eye bolts, regular eye bolt, and the rest are the parachutes and the drone.
Okay, so you have the bulkheads in there a little bit stuck right now, but that will need to be removed from the rockets in order for your parachutes to deploy.
Yes, but just right now that we're removing. Yeah, and we have the eye bolt that will be connected to the drogue and the main parachute inside the nose cone. So it's gonna be only 1 ejection, but 2 deployments events.
Okay, yeah, because you're using a tender descender, correct?
Yes, and we have the COTS redundancy for both the ejection and the tender descender.
Yeah, that was one of the things I wanted to talk to you a little bit about. I know I had emailed you after your second progress report where I was concerned with your diagram. And I saw in your third progress report, that you had added a tether between the two tender descenders to a different point on your rocket. And my concern is that you're going to have a really, really long tether to prevent any opportunity of a small piece of metal falling out of the air. And I'm just really worried about that line tangling with the rest of your recovery system or with your parachute. So if you have some more, if we're able to kind of pull out your
I
recovery
was
and lift a little
gonna
bit
address
quicker.
that like address that issue that you pointed out like in during the recovery presentation. So do you want to talk
Yeah.
about that while they're figuring out about the bulkhead?
Yeah, if you want to, I think that'd
All
be a
right,
good time.
so let me just open up the schematic real quick.
Okay.
So like we're on the same page. All right, so and also okay, so this is like our ESRA tender descender. It utilizes a rotor mechanism. And so like there'll be a quick link in here. So basically if we hook this up and we lock it in, now it's gonna lock like this, and there'll be a shock cord attached to this side of the ESRA tender descender, and it's gonna be actuated by a servo motor which will be mounted underneath this. We're waiting for like the actual piece to come back from the manufacturer so we can like take the dimensions of the whole thing again, and we can print like a casing for the servo motor accordingly. So according to the diagram, there'll be let me point it out. This second diagram, like the one that you pointed out, I think like you were thinking of like this type of tender descender where two sides are released, but in the ESRA ones, it's actually only one side which will be released, because this one is like the whole piece itself, and like solely this will be removed, and the floating piece that you were concerned about, it's attached to like a harness which is attached to this piece again.
Yes, if you still have, so if you have, can you connect them all together for you? You have them all in front of you, right? Your SRAD tender descender and that one. Yeah.
Yeah.
So if everything releases,
Right? Yeah. So should I add another quick link here, or like?
yeah, so that's where only if just the commercial one releases, this is what it looks like. But now when your device releases as well.
Yep. Okay, let me release.
So now you have that tender descender in your hand, right?
Yeah.
But the other quick link on that is left, right? That's with the rest of your shock cord. So that whole piece you have in your hand, if both of them release, are falling from the sky.
That's why there's a pink. I think it's kind of like confusing, but there's a pink harness here, which will be attached to like the core, like this is the core of the COTS tender descender.
So the COTS is always attached to the
the eye bolt in the avionics bulkhead.
And the ESRA is always connected to the attachment to the main.
Trying to trace this through in my head right now.
Yeah, it's a bit confusing, and
yeah, it's a little hard. Like it's definitely one of those things where it's easy if I have it in front of me. So if you're able to tell me there is no configuration based on this drawing that I had originally made for you guys where a single piece could fall from the sky. It doesn't matter how big, how small it is, right? I'm not yet convinced in my head that with this configuration, there's not something going to fall from the sky, but it is a little challenging because I don't have the pieces in front of me. So if you haven't already gone through that whole exercise of like, I'd love to see you guys put together your entire recovery harness, every single component, you know, connected outside of the rocket, and start going through your deployment events. So, you know, release one, then release the other, but, you know, try it the other way. What if only one releases? What if only the other released? And if you can go through that entire system on the ground and prove out that there's not a single configuration where you're not losing a piece, but there's also not a single configuration that would prevent the chute, the main parachute, from releasing, then I'm fine with that. And I think the best way to do that is with you know, pictures of the actual system on the ground.
So like, do we like demonstrate it through a video and like email it to you, or?
Yeah, if you guys want to do that, that would make me feel a lot better. Knowing that is taken care of ahead of time. Otherwise, I can almost guarantee that it'll be done in person on your flight safety review. And I would hate for that to be the first time that happens and an issue is caught there.
Yeah, we can record a demonstrating video and email it to you, because me myself, like communicating to you via email, it's kind of confusing what your problem is, and like it's hard to express like my solution through like drawings as well. So we'll make a video and email to you for your confidence in our recovery system.
Yeah,
Yeah,
that would be good. This is definitely one of those setups where it's really hard to describe on paper and it's really hard to describe verbally, and it's just so much easier to be able to physically show how the system exactly is in every possible way that the system could or couldn't work. So yeah, I think having a video would be great.
Okay, so like, is there any other concerns regarding to our SRAT components aside from like the configuration of it in the entire system?
Yeah,
Or-
I mean, I'd like to understand a little bit more about the testing you've done. My understanding is that you guys are going to be doing some testing or have been doing some testing using your SRAD device.
Yeah, so we have tested the mechanism itself, like the rotor latching mechanism, and we're waiting for like the actual piece to come back from the manufacturer. So there'll be vibration test as well, so to make sure like it doesn't disassemble like unscheduled, and we'll perform like load tests to make sure it doesn't fail as well, like using dumbbells and like attaching a shock cord and a dumbbell and hanging it like simulating in the actual flight situation. And we have done an static stress analysis here, and then the safety factor seems to and there's no concerns in safety factor.
What is that made of?
It's made of like the aluminum. It's made of aluminum 7075 for the casing, and the bushing will be made of nylon, because the bushing is just for alignment of the arms, like the moving parts here, like these two stuff. It won't actually like transmit or like receive that much load from the overall recovery system. So, and it's also like we'll make it by ourselves, like in-house, using our machine. And yeah,
So before the main parachute deploys, all the load is going through the COTS and the SRAT tender descender, right? All the shock load.
Yeah.
Okay.
And like the load will, like you can see in the yeah. The load is placed in this one where this will be hooked to a shock cord, and this will be where the quick link interacts with the component. And this here where my cursor is pointing right now, it's gonna be restricting the unlocking mechanism of the component, so it doesn't. It's designed to fail to not deploy, rather than like fail to deploy like without our control. So if we're talking about COTS, like we assume that the COTS will be working. So then even though this fails, it won't be unlocking. This
is non-pyro, right? This is
no, this is non-pyro. No,
this is 100% servo operated.
Yep.
And the mechanism that you've tested is it's a proof of concept mechanism, but the actual piece hasn't arrived, right?
Yeah.
So it's not really acceptance tested yet.
Not what tested?
It hasn't really been acceptance tested yet, like ready to fly.
Oh yeah. But like in the worst case, like if this actually like fails in any of our tests, we could
use for another tender
and
descender.
use a single COTS tender descender with double E matches. So
that's fine.
Yeah.
I think it would be nice for your COTS tender descender, regardless of whether you end up using your SRAD one or not, to use the double E match.
Yeah, we're using it regardless of the situation of the ESRA tender descender.
Good to hear. Okay.
Yeah, and so for our harness profile, we are using according to the specifications here, 35 feet, two 35 feet and 10 feet shock cords. The 35 feet is like according to like the rule of thumb where it's 2 to 3 times the whole length of the rocket. So it reduces the shock force and reduces the chance of our rocket colliding after the deployment. And we calculated our shock force by the governing equation here, the concept of like change in momentum before and after deployment.
I think your shock cord is well sized. I think your connections are pretty good sized as well. My biggest concern in the system right now, kind of like how Julian was saying, is that your SRAD tender descender has not been tested. So I'd like to see some more proof of that working ahead of the competition. So if you're able to do the testing under load, similar loading conditions to what it will see during flight, I'm worried about it taking the shock force, because all the load will be transferred through there for your drogue deployment. So if you can do some testing or prove out that can take that sort of a shock force, and that it can deploy your main parachute under load, if you've got some videos or other test data to show that would make us safety reviewers feel a lot better about the SRAD system, because not only do we want it to deploy, but we also really don't want it to deploy early. We do not want to be having a main parachute out prematurely because this device, for whatever reason, may potentially fail. That's really, I think, my biggest concern is not that it won't deploy, because your COTS one should, all things considered, always deploy. It's really that this one would let the parachute go too early, and then you'd be drifting for miles and miles and miles and potentially breaking our horizontal waver.
Yeah, we once the actual piece comes to our hands, I will test it immediately and update you regularly. And like as I said, we already we simulated our component through FEA analysis, and as of now, that's like the most we can do while waiting, and it seems to not have too much concerns aside from like the configuration thing, which we'll send you a video of.
Yeah, and so where is the servo then mounting to the ESRA device, and then where is the other side of that servo mounted to? Like, is it fixed to the rocket body, like a bulkhead or something?
So we'll actually make a case for the servo to like stay aligned to the arm whenever we want it to unlock, we are sure that like the arms are aligned to the unlocking part of the component. So it's gonna be something like this, mounted. So we're just waiting for the actual piece to come back so we can figure out the dimensions and 3D print a case for it to sit underneath the component.
Hey, so there's going to be a PWM cable from your computer all the way throughout the shock cord, all the way to the servo, right?
This piece is gonna be like sitting around like on the bulkhead. So like there'll be like a cable extending into this whole system here. But like we will make this like longer so it doesn't come into tension, and the whole
if
tension
it
forces will
starts
be
tangling, you want to put a lot of slack in there.
yeah, we're gonna slack it. So like the whole tension forces will be transmitting through the shock cords.
And then your connection ports, is it just a standard servo plug?
Yep. Just the standard one.
You're gonna hot glue it, or electrical tape or something?
So the flight computer
เราจะ connect ช่วยยังไงมันจะดีซับไหม
yeah we will use a Molex microfit connector from the flight computer and connects it to the place where the servo will mount. So the flight computer will features two PWM channels and will be connected via Molex microfit to the
So there'll be a D-sub panel on the avionics bulkhead, which the wirings will be connected from the recovery bay into the avionics bay via the D-sub on the bulkhead.
So you can replace those cables without having to open up the entire AV bay, right?
Yeah.
Okay.
So your servo is only controlled then by your SRAD avionics, correct?
Yep.
Have you been able to get a test flight in for your SRAD avionic unit?
yeah, we have tested both the pyro and servo outside of the rocket assembly, but we're waiting for the manufacturer to send the final version of the flight controller to the final iteration has been tested. So yeah.
But have you actually flown it on a rocket before?
No.
So we tested our flight computer using a drone, just like because in Thailand we can't launch an actual rocket, it's like illegal. So the most we can do is by drone, and we're waiting for the final iteration of the flight computer to be sent back to us, because we just we just improved the final one which we're ordering right now.
Yeah, but we have tested the latest one already.
Okay, so when this flies on your IREC rocket in Texas, that will be the very first time that the flight computer has flown on a rocket, though. It'll have flown on a drone, but it would have never flown on a rocket before.
Yes, similar to a couple of last years.
But
most of the logic has been flown on last year, right? You're not really changing that.
Yeah,
Yes.
the logic is pretty similar to
Okay.
the previous years.
What has changed then? What is the difference between the version that has flown on a rocket versus what you're gonna plan on flying this year?
This year we will have servo for the ejection. Also this year we changed from cost components like microcontroller and other sensors to fully SMD, which we design and send to manufacturer, and we assemble it ourselves. But yeah, that's pretty much the difference between last year's and this year. But the
So
logic,
last
yeah,
year's
yeah.
is all breakout boards, and this year is, everything surface mounted, custom.
Yes.
Okay.
Yeah, but the logic is similar to last year's.
So kind of the thoughts I'm having right now and the struggles I'm having is according to our design test evaluation guide, if you're going to use a flight computer to deploy any event, if you're going to use it for any parachute deployment or whatnot, it must have been test flown. And unfortunately, a drone would not really count for that. Like drone is a good way to get some testing in, but it's just not really quite the same environment as you would see on the rocket. It's got different acceleration, different flight profile, all of that. So my concern is, I mean, one, that it's not meeting that DTAG requirement of the flight computer must have been test flown. I get that it's a similar iteration, but even more minor changes, we really would like to see a test flight. I do understand it is quite challenging for some of our international teams to have the opportunity to do those test flights, which is really quite unfortunate. So often what we would recommend doing is if you're going to make a big iteration or you're going to make a new flight computer is to fly it in your rocket, but not have it connected to any deployment devices so that, this year you would be able to get that test flight done. And then next year you would be able to use it to deploy whatever you want, just so that it is proven. Because the whole concern there is there something new? Is there something different with this flight computer that could cause issues, right? Could it cause your rocket to separate prematurely or not at all? Same for your tender descender. And so having an SRAD system that's not proven out causes us a lot of worry. I hope you kind of understand where I'm coming from here.
So basically the difference between this year and last year is just servo this year. So yeah, like what you said, we haven't tested that mechanism from previous year. So but we cannot test rockets in Thailand. So yeah.
But like talking about your premature deployment, so the only thing that I could think of right now that will cause the premature deployment is the ESRA tender descender structural failure, not like the the actuation by the ESRA flight computer. Because like if it can't detect like the altitude that it's supposed to deploy, it's actually the COTS that will be the redundancy to that deployment rather than the failing in case of the server actuating by itself, if you get what I mean.
Yeah. I definitely get what you're understanding. The flight computer shouldn't be able to theoretically cause any issues, but since it hasn't gone through the full scope of testing, I think we can always say there's a risk, right? The more we test, the more we reduce our risk. Without as much testing, there could be undiscovered, errors or bugs or whatever it is. And so it's a little bit of a gray area, right? Because you've flown a very similar flight computer, but you haven't flown this flight computer before. I don't really want to be the one to tell you that you can't. So I think to help sort of make that decision a little bit easier, what I would like to request from you guys is if you could write up a note to me so that I can send it over to our lead range safety officer, and just in that note include a little bit more details on whatever flight computer that you have flown before at previous IREC or wherever. What are the differences between that one and what you're doing this year from a firmware point, a hardware point, a software point, right? Any of the differences in there, as well as the additional testing that you've done this year. And then we'll look kind of at that comprehensive list of what has successfully test flown on a rocket, what is new, but has been tested in other ways. Kind of with our risk analysis, does that mean that sufficient risk reduction has taken place to allow this to fly? Because it would be an exception to the rule if I'm trying to lay down the law and enforce the rules, which the rules are hard to write because there's so many different edge cases and, well, what if this, right? So I think that that's kind of our best path forward, is to get just a clear email, or short document. I don't need a really long report, just, something brief that goes into those details, so that we can kind of look at it as a range safety team. And I'll bring it to Jim Jarvis. He's our lead range safety officer for this year, and let him kind of have that final say on if we can do that or not. Because ultimately, like, I want you guys to be able to fly your SRAD flight computer that you've worked really hard for. I understand that, like, that's controlling your servo, and we want to use that to deploy your SRAD tender descender. So there's a lot of interest in wanting to be able to fly it, and it would be cool. But I think in the terms of safety, in the whole risk reduction standpoint that we have to take for events like this, I think that's our best path forward. Is that something that you guys think you could agree with for that?
I mean, if that's the only way that ESRA would accept our flight computer this year, so we should accept. We should go through your way, your suggested way. But like,
yeah, that's kind of the best path forward I would see there.
I have another question. Like, if somehow we use the same flight computer we used last year, but we find some other, like, some way to convert, like, the E-match actuation to actuate a servo instead, will that be accepted?
ในเซิร์ฟเวอร์กับพี่แมชมันเหมือนกัน
มันมี converter ได้ไม่ใช่ที่มันเป็น pulse แล้วมันเป็นอันนี้
ไม่แต่มัน
I'll put it this way. I would rather have a system that was meant to do the job of deploying the servo than an old system that, just because it was test flown, we're going to try and compile something and throw something together just to say that, oh, it meets the guidelines, right? Because whatever you're going to add would kind of be either some sort of like an addition or potential modification to that flight computer.
Yeah, so they're basically both new.
Yeah, so like personally, in that sense, I would almost rather you use the flight computer that you've ground tested a whole bunch and have made for this very reason. It is just kind of like, I said some of the concerns earlier.
All right, so
yeah,
we'll write a note through your email, so like you can let the range lead review it again.
Yeah, and I can send the note to me and include Julian on there as well, and I'll loop in the range safety officer and sort of fill him in on kind of where we're at and why we're trying to make this decision as well. But include whatever information that you can on the differences between those flight computers, the testing that you've done, just so that we can make the informed decision on what is going to be the safest, but still allow you guys to use the hardware that you've been working on so hard all this year. Like, I understand that you've put a lot of work into this, and I don't want to just brush that all aside. And I don't really think that that's fair either. But from my point, where I have to be like, safety is the most important thing, I must enforce the rules.
Right, we understand.
If I'm on that point, then I have to say no right now, and I don't want to do that right now. You see what I mean?
Right. Okay, so we'll keep that aside for later. But right now, do you still want to see our nose cone section? We actually figured. All right.
Yeah, if you could, that'd be good.
Erica, I'm their advisor. Can I just ask, so the possibility is that they submit a request to basically bypass the rule and it gets rejected? That's possible, right?
That would be. I think it just kind of depends on the details, right? And I'm really going to leave that decision up to Jim Jarvis. I would like to try and convince him to say, hey, look at all this work that the team did. Like, they've done a lot of work to prove that it's safe, but it doesn't meet the rules that we're requiring for launch. He gets the final say. Like, I'm going to try and push him to see if we can get there. So yeah, ultimately the answer could be no. I would not like to focus on that right now. I'd like to focus on what can we do to say yes, that the system, is a little different from the rules, but is still equally as safe.
Okay. So let's hope it's not no then.
Yeah, that's why I don't want to say no right now, right? I want to have a further discussion on it first before I say no, right? And loop in some other folks in the competition who have a higher stakes in terms of safety in those regulations. before we, you know, do anything extreme like say no or blindly say yes without having the full scope of the details.
Yeah, okay.
Yeah, so I'm reading in the test and evaluation guide. Yeah, I see a statement under SRAT. Electronics says teams shall provide proof of function of SRAT flight computers, including ground testing and flight testing before the competition. But you say it has to be flown on a rocket, right?
It would, right? You know, honestly, when I had seen that you guys said that you were going to flight test it on a drone, I did kind of think for a minute, I'm like, is that acceptable? But I don't really think that that would meet the intent of the written rule because it wants it to be flight test on a rocket that would have a flight profile similar to a rocket, right? A high acceleration, a coast, you know, that sort of velocity profile that you really just can't get with a drone.
Yeah, the only way I see to get some sort of useful data is if you tweak some of the parameters, like say, okay, launch detected instead of 5Gs, maybe you just put it to 2Gs and try and emulate that with a drone, along with, you know, apogee detection schemes and main altitude, and then you change that for the rocket. But other than that, the best way is to just fly it on a rocket.
Yeah, and especially because when you fly it on the rocket, you get the testing of the full picture of the flight computer, right? It's not like we're testing part of it with this and part of it with that. It's like the whole flight computer is done and we are proving that it works. So yeah, I think that there could be a path forward. I'm not going to promise anything. I'd like to think that there's a path forward here because you guys, you know, it's an iteration of a previous computer. It's not a new one. All
When
that as we've already
when do you think the computer is going to be made?
Again, please.
When do you think you'll get that flight computer done?
Okay, so we have like a lot of previous iterations, but the latest iterations with only like some optimizing the wiring, it's gonna be arriving in like a week. Like a week or two later.
Okay.
Yeah.
And then how does that include all of your sensors and everything soldered, or these are just components and you have to solder everything together?
What the manufacturer will send us is like the bare PCB, and we will assemble it ourselves, but that should take
Okay.
like less than a day to finish.
And we already have all the components in hand.
And
Okay.
every component have been tested to work electronically. So yeah.
Okay, cool. Just yeah, get that done as soon as possible and just wait for what they have to say.
Okay, sure. I'll bring you to the nose cone.
Okay.
So this is where the avionics box sits on top of the coupler. And once you remove it, you will see like the drone parachute and the main inside.
Yeah, and we have a we'll have a bulkhead at the end connected to a stud and a to the nose cone at the very top.
Big swivel in there, right? Is there a swivel?
Yes, there will be swivels on both the drogue and wing.
Yeah.
On the bulkhead in the nose cone as well?
Yep.
Yes.
Okay. Yeah, the nose cone is going to separate from that coupler, right?
Yes.
Yeah, the one that you're holding.
Yep. This one.
How far does that go into the nose cone? And it cannot bind up, right? Because typically you try and slide a coupler up in the nose cone, you know, if it goes too far, it's going to get stuck. So you have that only extended on the straight section of the nose, right?
Yes, only the straight section. And I think we just need like some minor sandings at the rim of the bulkhead that just comes.
Okay, good.
Is the bulkhead connected onto that coupler during flight?
Yeah, yes. It's gonna be connected via a stud of the avionics bay.
Okay.
Yep. So it's gonna be connected here. So it's gonna be this one's gonna be inside, and the bulkhead's gonna sit up here.
So the whole module will be under compression.
Okay, sounds good. I do have a few questions too on the avionics bay that you're holding in your hand there. What are the batteries that you're using for all of your flight computers?
Battery's gonna house it back here, and it's going to be. We'll bring it up.
We're using this battery MINR 21700 from Samsung. It's 3.7 volt, 5,000 milliamp hour battery.
Okay, and then do you have that like snapping into some sort of like a case? How are you physically retaining that and connecting that to your flight computer?
We will have a 3D printed ABS case, and it's going to be housed at the back of the avionics bay. Yeah. Inside this slot.
Okay.
Yep. And the battery draining is like 72 hours.
Yeah.
Yeah, around like 70-ish hours.
Okay, sounds good.
Yep. And
Yeah, I think that's
all for nose cone.
yeah. I think my biggest questions regarding just the nose cone and the avionics still is, like I mentioned, having a good sort of walk through, for you guys as well, so you truly understand every possible scenario of how your recovery system can deploy, but also so I can better understand with that visual representation of, when everything's connected to the bulkheads and whatnot, how that all deploys will definitely help finish painting the picture there.
Okay.
All right, I think that has covered most of my main questions and concerns on the rocket. Julian or anyone else, do you have outstanding comments, questions, or concerns as part of this rocket review?
Just keep me updated as much as you can, especially after your parts have arrived. It's been a bit quiet lately, but once your parts have arrived and you guys have everything fabricated, just send some pictures along.
Okay, sure. In fact, we just finished our finals exam last week, so yeah, we are full on right now.
Okay, good. Yeah, I got my exams too.
Yeah,
Also,
okay.
it would really help if you guys go and look at your past year's flight review sheet. Things that they have you corrected before they can sign off on your rocket from previous years. Typically it's like a wiring thing, avionics bay wiring thing, or I don't know, a rail button, vent holes, things like that. I know for the past few years, we typically launch on like the last day or like the day before the last day. I can't remember. So if you can iron all of those things out and not have any last minute, emergencies or last minute big fixes, all you do is just show up, turn on a switch, and it's ready to fly. That would be nice.
Okay, sure.
What type of switches are you guys using? Speaking of switches.
We'll have a turnkey and a pull pin. The pull pin's gonna be for the ESRA flight computer, and the rest gonna be the turnkey.
Okay.
For the air brakes also?
Yes.
Okay.
All right, yeah, I think that covers my main concerns for the rocket. Kind of as a recap, the few things that we're looking for first is that that some more details, descriptions that I can pass on to our lead range safety officer regarding your flight computer and try and get that exception to the flight testing rule for that. And then would also like to see, kind of like Julian was saying, is as you're getting in some of these components, you do have a lot of components, my understanding, that you're waiting for to be machined, your fins, your transitions, a number of other parts. When you get those in and you get those sort of tested and all assembled, I'd love to see some photos, making sure that those are just all fitting and coming together as expected. I'm gonna double check my notes. I think there's a couple other things. The video with the recovery setup. And then hopefully some more details and videos of that SRAD deployment device testing. There was one other thing I wanted to ask you about, and that was you're using CO2 ejection for your separation, is that correct?
Yes.
And so you have an SRAD device for deploying those CO2 cartridges?
Yes, SRAD and a COTS redundancy.
Okay, so you're using both a COTS and an SRAD solution for those.
Yes.
Okay, that's good. I like that you're using kind of one of each. Do you have anything here in front of you today that you can show me for your SRAD CO2 ejection system?
Oh, the SRAD is on the same batch. So like we order like a very big batch, but we have a COTS right here. It's a Eagle. Do you want to see the SRAD ejection prototype?
Yeah, if you do. I'm most interested in your SRAD run. The COTS ones I trust that you can set up and run correctly. But I'm most interested in the ones that you guys have made yourselves. And I have been looking at all of like the CADs and documents that you have been sending me over the year, and it looks overall like a good design, but just wanted to see if you guys have physically gotten them made and have done testing with those yet.
Okay, so yeah, I think it's the same case as the other ejection SRAD tended descender. Yeah, so we're waiting
Okay.
for the real piece.
Yeah, so this is a 3D printed prototype. So this was optimized from last year's ESRA ejection CO2 ejection device, where it utilizes CO2 to separate the rocket as well. So you can see the thread here. This is where the CO2 will be threaded into the device, and this pin that can be moved up and down. It's actually gonna be powered by a spring to strike the seal on the CO2 cartridge, and there'll be two locking mechanisms. So the first one is it's gonna be the lock mechanism of the pre-compressed spring pin is gonna be actuated by servo motor. So once the servo motor turns, it's gonna unlock this lock, and the hole here of the pin, it's gonna be released, and the pre-compressed spring is gonna help this rod to strike the seal on the CO2 cartridge. So it's
So
there's black
right?
powder involved in the whole system.
Yeah,
No
it looks like a
problem.
very interesting device. And I'd love to see some videos of the testing that you're doing for that when you get all those final parts in.
All right, we'll keep you updated.
Yeah, and so I'm assuming then you also haven't done, or have you done separation testing with?
We did. Do you want to see like the video now, or we can send it to you via email later of the?
You can just send it to me later. I just wanted to check and see if you had
Yeah, we
gotten
already
that.
performed the rocket separation ejection test.
Okay.
Yeah, so there's nothing to worry about in terms of like the shipping sharing at apogee, and about the premature ejection due to pressure difference in the rocket. Our shipping calculation is explained in the technical report. So if you have any concerns in that, you can email us as well.
Okay, just a quick comment on that. Did you take into account the maximum drag that your air brakes could have when you were determining those shear pin sizes?
Maximum drag. Maximum drag on the air brake.
Like drag separation as well.
Yeah, drag separation, since your air brakes are going to suddenly a lot more
I
drag.
try to include that into the spreadsheet calculator, and it seems to have like a negligible effect compared to the pressure difference.
Okay. Are you venting your area where your parachutes are?
We are venting, but I assume worst case scenario during the calculation. So I assume all vent holes are clogged.
Okay. I'm surprised that your air brakes don't really impact that. Usually they do have at least a little bit of impact on the total drag if they're fully deployed at the worst point in your flight, just in terms of the additional
I'm using
drag.
the M4 nylon shear pins, 4 of them. So like the safety factor, then it decreases from like 2 point something to around 2. So like it's still in the safety margin.
Okay, I
Yeah,
see.
but
So
I haven't just include that part in the technical report. But like if
I
you want
understand.
the detailed calculation again, I can send it to you.
Okay, yeah, I'll maybe take a peek at what you put in your technical report, and if I've got more questions, I'll let you guys know. But
Right.
as long as you've considered it and you've done the math and you've made sure that they're sufficient, then that makes me happy.
Right.
Okay. I think for real this time, I am done with my technical questions. Any other technical questions before I ask a few non-technical questions?
No, I don't think so. But if we have, we'll email you afterwards.
Okay, yeah, sounds good. And same for Julian or anyone else if you've got any comments or concerns. Always good to bring those up at any point in time. Okay, so moving into some more logistical questions for your team. Do you guys have all of your travel booked for the competition?
Yes, our air tickets have been paid. We have acquired all of our visas for our fly-off engineers, and
all
yeah.
of our accommodations are booked as well. We have everything in place.
Okay. And for shipping your rocket, are you taking that as carry-on or checked luggage, or are you shipping that separately?
We'll bring this green container. It's gonna we'll load it on our plane.
Check
Okay.
luggage.
Sounds good. All right. And you've traveled to the competition before, so I'm sure you're well familiar with whatever you need to do to make sure that that has the highest chance of success of passing customs and have all your necessary paperwork on hand.
Yes.
Okay. Are
Yeah, just have
you
as much paperwork as you can, proof of stay, when you're gonna leave, all that. Border security is different these days, so just yeah.
Okay.
Yeah, Julian brings up a good point. I know some other international teams for the competition, they are bringing more paperwork than would ever imagine necessary, but definitely things like proof of your accommodations, proof of your return flights, of course, your visa information. Some folks are even bringing things like vaccination status, the letters from the competition, the letters from your university. The more the better. I hope that nobody runs into issues, but I don't really have a good grasp on how bad it could be. So better to be over prepared than under prepared.
One quick question. Like right now we have the invitation letter that contains the names of the individuals going to the competition. But when we request it, I think there's a prompt for the only names for people that haven't got a visa yet. So there will be only like 9 names on the invitation letter for now. But so that's the letter with the name, and we got another invitation letter with our team name, but there's no like individual names. So my
Yeah,
question is, should we like ask for the invitation letter with names for all of our staff going there?
honestly, I'm not sure what our standard is if we usually have the invitation letter with all the team member names on them. If you'd like, you can definitely email that general.info@esrarocket.org email if you'd like to just double check, see if they can provide that for you. Maybe that's a good thing to have, or maybe that's completely unnecessary. I'm not an expert on that, nor am I an expert on sort of visa in border crossings in and out of the US. So
Okay.
in the effort of better safe than sorry, I think you should at least ask for it and we can see if our admin team can provide that to you.
Okay.
Yeah, I think it's better to try to get it because if you have some team members that names are not on the list, I would assume the worst thing will happen and you'll have a problem. So try to get as much extra information as you can.
Okay. And the invitation letter with names. Last time that we requested, we were waiting for like 1 to 2 months for it, and like we already emailed follow up for like 3 to 4 times for it.
Okay, if you email again, you can CC me on the email, and if I don't see a response come through within a week or so, I'll try poking some of the people on my side to get that
Okay.
moving along.
Sure. Thank you.
Yeah. Okay, so I know you guys have been to IREC before, but obviously this year we have a new site. Are you guys up to date with where the launch site is relative to where the convention center is and all of those details?
Yes, so the launch site is going to be around 2 hours from Midland.
Yeah, about 2 to 2.5 hours. There's a lot of dirt roads that you have to travel on that can be a little slow going as well. So, are you guys staying in Midland? Are you staying in a different city?
We're staying in Odessa.
Okay, for the whole week.
Yes.
Okay. All right. I'm not sure how much you've looked into it. I like to always remind students about the weather and what to expect, again, especially since it's a new site. Expect the weather to be, I would like to say, just as bad or worse as it was in Las Cruces at Spaceport America. It will be hot. I know you guys work in Celsius. I don't know the Celsius numbers, but 110 degrees Fahrenheit or even hotter potentially some days. So it could be quite brutally hot. We are potentially expecting winds to get a bit high into the afternoons. You know what, we'll never know until the day of, but especially with you guys being a 30K team, would definitely recommend you trying to be as early in the day as possible. There is no early launch day bonus this year. So we're trying to reduce like the mass hysteria rush on the first day of launching. But that being said, I would encourage you to try and still be ready to launch as early in the day as possible. We'll be having an overnight quarantine system similar to last year, where if it's near the end of the day and you're ready to launch, you get your rocket checked off. And if there's just not enough time to launch or the winds have gotten too bad, we can put your rocket in an overnight quarantine, which means you have to leave it overnight. You can't touch it, but you will be able to launch very first thing in the morning then the next day. So I'd encourage you to, work that into your logistical planning of how you're assembling your rocket. If you're able to have it fully assembled, turned off, and just sitting there for up to a day, that would be most beneficial to get you guys launching earlier in the day rather than later in the day.
Okay.
All right, and then you got your motor. Are you picking that up once you get on site, or is your flyer record grabbing that for you?
We're picking it up on site. We have purchased it from Wildman Rocketry.
Okay, sounds good. All right, I think that wraps up all of my questions. I'd like to turn it over to your team or anyone else here in the call. Do you guys have any questions about the competition this year? Any changes? Anything and everything?
Oh, what about the gate opening policy? Is it like similar to last year?
We're still nailing down the exact details. We're expecting that the gates will open at about 5 a.m. every day. The security is a little bit different. Previously at Spaceport America, that was a very secure facility. Where we are this year is really just in the middle of nowhere, and there's a couple roads to get there. And so we are going to be pretty strict that you're using the entrances we designate. Well, keep an eye out on HeroX. There will be more information sent over the next few weeks leading up to the competition. We will have like traffic control there that will try and prevent people from getting in really early. We don't want teams showing up at 4 a.m. just to be the first in at 5 a.m. It just really doesn't get you anything this year. But about 5 a.m. is when gates will open each day. The flight safety reviews will open at about 5:30 to 6 a.m. every day. And we're hoping to have the first launches going off by 7 a.m. most days. The exception to that is Wednesday, since it's the first day, and we have nearly 3,000 people coming out to that launch site for the very first time. We're expecting to start up a little bit later, just in the launching. We're still planning on trying to open the gates early at 5 a.m., but just to make sure that all the gears are turning smoothly, we may start launching just a little bit later on Wednesday.
Okay, and the big tents are being brought from Spaceport facility to the new one, right?
Yeah, they were just rented from a local event contractor last year, so they weren't at Spaceport, but we are going to be having similar tents this year as we did last year. Yeah, so everybody will have a spot allocated underneath those really large tents, and then you will also be provided 2 folding tables. If you want more, you'll need to bring them yourselves. We aren't providing any chairs, so if you want those, also bring those yourselves.
Okay, thank you.
I would like to ask about like the regulations using the hand radio amongst like ourselves.
Yeah.
is there any restrictions to that?
So there is not generally, we will be having a frequency allocation form going out. My understanding is within the next week, similar to last year, where you include what frequencies your flight computers are going to be on. And that's also the spot where you would indicate if you're planning on using any handheld radios, whether they're on just like standard FRS, GMRS channels, or even if you're planning on using a ham radio to communicate amongst your team. So definitely look for that and fill that out to the best of your ability. I will say that a lot of those unlicensed radio bands get very, very populated. There's just not enough for every team to have their own at the competition. So teams will just have to share them to the best of their abilities. So just something to be aware of, but there aren't any specific restrictions against using them.
All right, thank you.
Yeah, I think that's it from our team.
Okay, great. I'm really excited to see this kind of get wrapped up. I know you got a few more parts you're waiting on to get this whole rocket completed, but I can imagine once it's done, it is going to be a very exciting flight to watch. So congratulations on all your hard work. I know you guys have a little bit of work left to do over the coming month. But I can really see the hard work that you guys have been putting in so far, and I'm really impressed with what I've seen. And minus, we got those few other things we got a little bit of work on. I'll probably send you a follow-up email just after this meeting, just kind of reminding you of those, make sure we're all on the same page of what I'm still looking for and what you guys are going to provide. And then once we're done here, you can also finish up the recording and get that sent off to the general info email as well, so that can be recorded.
Okay.
All right, yeah, and if anytime you guys have any more questions about the competition or your rocket or anything else, please don't hesitate to contact me.
Okay, sure. Thank you.
Yeah. Bye-bye.
Bye.
Thank you. Bye-bye.
All right, see you guys.
All right, see you.